Hello and welcome back to 8701. In this class we'll talk about spin. If you remember the discussion on relativistic kinematics we had last week, you noticed that I discussed the decay of a pion, say a neutral pion, into an electron and a positron and an electron. And we were able to calculate the velocity of those two particles, the electron and the positron, quite easily by knowing the mass of the pion and the masses of the electron and the positron. You put yourself into the rest frame of the pion, and you can calculate those velocity. I also told you that this decay is highly suppressed because of the spins of the particles involved. The pion has a spin 0, and the electron and the positron have spin 1/2, but it is not easily possible to align the electron and the positron such that the spins align to 0. So therefore this decay is not easily possible. But let's dive a little bit into this. In quantum mechanics, the spin of a particle with a vector is quantized, and in terms of its length and its components. If we calculate the length of the spin vector s, we find that it's square root of s times s plus 1 in units of h bar. The components then along the any axis actually, and in this case here the z-axis, have eigenvalues, and they're listed here. And we find that there's 2s plus 1 possible values. So I'll pick here just arbitrarily the z-axis, but the question is an obvious question. Which axis is a sensible choice for this problem? So I want you to actually stop here and think about this. What are sensible options, if you want to get an eigenvalue, the physical state of particles, which axes are the right ones to choose, or sensible? There's no right and wrong in this discussion. Let me motivate this. If you look at the orbital momentum of a particle, that's given by r cross p, where p is the momentum vector of the particle. So now if you're looking at the total momentum, we have to add the angular momentum and the spin of the particle together. So as shown in this picture here, you see that the parallel component, the component in parallel to the flight direction, is 0 by definition, because the cross product is defined, the angular momentum is defined as a cross product with the momentum. So this is a nice choice of coordinate system or of axis, namely the choice of the momentum of the particle. So you find that the total momentum perpendicular is the spin of the particle perpendicular, and the transverse component is the angular momentum, the orbital angular momentum, and the spin of the particle in transverse direction. This then immediately gets us to a new definition, that of helicity. We can define the helicity of a particle as a spin of the particle dotted with the momentum of the particle and then normalized by the momentum. So you basically, for a fermion, which has a spin 1/2, get plus 1/2 if the spin points into the momentum direction, and minus 1/2 if it points in the opposite direction. So now if you go back to our particle here, out by 0, decaying into an electron and a positron, spins are 1/2, but you find that an electron is a left-handed particle, so its helicity will point in this direction, and for the positron, it points in the same direction. So the pion here is spin 0, and if you discuss this in the rest frame of the pion, the electron and the positron fly off in opposite direction, and which means that the spin doesn't align to 0. So that's why this is highly suppressed. It's not 0 because you can put yourself into a rest frame where you're just basically looking both particles from one side, they're both coming to you, and in that case it's allowed. But the spin configuration is highly suppressed in any case.